me show you how to be a good Bayesian. Change your predictions.
So I'm curious if you can define what a deep Gaussian process is, because I think my audience has a good idea of what a Bayesian neural network is, and I've had, especially recently, Vincent Fortwin talk about that on the show, so I'll put that also in the show notes. So these Bayesian deep learning, I think people are familiar with. Can you tell us what a deep Gaussian process is? Because I think people see what a Gaussian process is, but what makes it a deep one?
Great episode, the one with Vincent, by the way. I checked it out. And,
Thank you.
Because I guess he would say a lot of things that I would probably say also in my episode. So it was great to see it. So a Gaussian process, there's many ways which you can see it. The easiest way is probably to start from a linear model. I think I really like the construction from a linear model. So if we start from a linear model and we make it Bayesian, so we put a prior on the parameters, then we have analytical forms for the posterior, the predictions, everything is nice and Gaussian. And so now one nice thing we can do is to start thinking about linear regression, but now with basis functions. So we start introducing linear combinations, not of just the covariates or features, or if you want to call them that, but you have a transformation. Let's say sine and cosine, could be trigonometric functions of any kind, could be polynomials. And it turns out that you can use kernel tricks to be able to say what the predictive distribution is going to be for this. The model is still linear in the parameters, but now what we can do is to take the number of basis functions to infinity. So we can make an infinitely large polynomial. And now the number of parameters will be infinite. But what we can do is to use this so-called kernel trick to actually express everything in terms of scalar products among this mapping of inputs to this polynomial. And so if you do that, then what you can do is to, instead of working with polynomials or these basis functions, now you can define a so-called kernel function, which is the one that takes inputs, features, and it spits out a scalar product of these induced polynomials in this very large dimension, infinite dimensional space. So this kernel trick allows you to just then work with something which is infinitely powerful in a way, because it's infinitely flexible in a way that you have an infinite number of parameters now. But the great thing is that if you have only n observations, all you need to do is to care about what happens for these n observations. And so you can construct this covariance matrix, and you can do, and everything is Gaussian. Again, it's very nice. So the first time you generate a function from Gaussian process, it's beautiful because you get these nice functions that look beautiful, and it's just a multivariate normal, really. And it's just, that's all it is, So I still remember the first time I generated the function from a GP, because it was a eureka moment, where you realize how simple and beautiful this is. And now, so then you can think that now this represents a distribution over functions. So if you draw from this GP, you obtain samples that are functions. And now what you can do is to say, well, what if I take this function now, and instead of just observing this function alone, I just put it inside as an input to another Gaussian process. So in a GP, you have inputs which are your input data where you have observations. So now you're mapping into functions, and then this function can become now the input to another GP, for example, And then you can even say, okay, let's take these inputs and map them not just to a univariate Gaussian process where we have just one function, but maybe we can map it into 10 functions. And then these 10 functions become the input to a new Gaussian process. And so this would be a one-layer deep Gaussian process, right? So you have now one layer, which is first hidden functions that then enter as input to another Gaussian process. What's the advantage of this? Why do we do this? Well,
yeah.
With Gaussian
processes, be my question.
Yeah, so with Gaussian processes, the characteristics that you observe for the functions that you generate are determined by the choice of the covariance function. So if you take a covariance function, which is RBF, you're going to have infinitely smooth functions that you generate. And the way these functions are going to be the length scale of these functions and the amplitude, they're going to be determined by the parameters that you put in the covariance function. And of course, there might be problems where, you have non-stationarity. So in a part of the space, functions should be nice and smooth. In other parts of the space, maybe you want more flexibility. And then, a Gaussian process with a standard covariance function cannot achieve that. And so in order to increase flexibility, you either spend time designing kernels that actually can do crazy things, which is possible, but relatively hard because now you have a lot of choices. You can combine kernels in multiple ways. And if you have a space of possible kernels you want to choose from, combining them, becomes a combinatorial problem. So you may say instead, let's just compose functions. And composition is very powerful. And this is why deep learning works. Because in deep learning, you essentially have function compositions. And so even if you compose simple things, the result is something very complicated. And you can try it yourself, take a sine function and put it into another sine function. If you play around with the parameters, you can get things that oscillates in a crazy way. And this is very simple, but very powerful. And so the idea of deep Gaussian process is exactly this, to try to enrich the kind of class of functions you can obtain by composing functions, composing Gaussian processes. And of course, now the marginals, in a Gaussian process, all the marginals are nice and Gaussian. If you compose, these marginals become non-Gaussian. And this is really, getting to the point where you start thinking, well, why should we then restrict ourselves to composing processes that are Gaussian? Maybe we can do something else, And then, maybe thinking about other ways in which you can be flexible in the way you parameterize these complicated conditional distributions.
Okay, yeah. Damn, this is super fun. So it sounds to me like Fourier decomposition on steroids, basically. So it's like decomposing everything through these basis functions and plugging everything into each other. So like like these mamushkas of Gaussian processes, basically. So yeah, and I can definitely see the power of that. It's like, it's like having very deep neural networks, basically. So I definitely see the connection, why that would be super helpful. And that helps, I'm guessing that helps uncover very complex nonlinear patterns that are very hard to express in a functional form. That functional form would be, well, you have to choose the kernels. And sometimes, as you were saying, the out-of-the-box kernels can't express the complexity you have in the data. And then having basically the machine discover the kernels by itself is much easier.
Yeah. And it's really also about the marginals. If you believe that your marginals can be Gaussian and you're happy with that, then it's all fine. You can do kernel design. You can spend a bit of time trying to find a good kernel that gives you good fit to the data, good modeling, good uncertainties. But then there's still going to be this constraint in a way that you're working with the Gaussian process. In the end, marginally, everything is Gaussian. You may not want that in certain applications where maybe the distributions are very skewed and other things, And then maybe the skewness also is input dependent, So this non-stationarity also, again, you can encode it in certain kernels, but it's just so much easier to compose. I mean, from the principle of just mathematical composition. Then, of course, computationally, how to handle this is another pair of hands.
Yeah. No, exactly. I mean, you're trading basically something that's more comfortable for the user for something that's much harder to compute for the computer. But yeah, like in the end, that also can be something that is more transferable, because if you have, unless you're a deep expert in Gaussian processes, coming up with your own kernels each time you need to work on a project is very time consuming. So it can be actually worth your time to turn into the deep Gaussian processes framework, throw computing power at it, and go your merry way working on something in the meantime while the computer samples. That definitely makes sense.
But again, the deep aspect carries other design choices. Now you have to choose how many layers, what's the dimensionality of each layer. So
yeah,
and then there is this other problem of now what kind of inference you choose, which definitely has an effect. So we've done some studies on this, trying to compare a little bit various approaches. I mean, we did this a few years ago now because the deep, I think we started working on this right after TensorFlow came out. So this was 2016. So we did our deep GP with a certain kind of approximation that is not very popular. I mean, the community seems to have agreed that, inducing points methods are very powerful to do approximations. And, I've also done some work on that with some great people, particularly James Hensman, who has developed GP Flow with some other great guys. And but random features is what you said before. You mentioned the Fourier transform on steroids. I mean, the idea is really to for certain classes of kernels, you can do some sort of expansions and sort of linearize the Gaussian process. So before I was talking about going from a linear model to something which is infinite number of basis functions, and now the idea is just truncate this number of basis functions. You can do it in various ways. There is a randomized version that we do when we do these random features. And then you sort of truncate. And so now instead of working with this, you turn a Gaussian process into a linear model with a large number of basis functions. And then linear models are nice to work with. And then if you compose them, then that's when you get the deep Gaussian process. Essentially, you get a deep neural network with some stochasticity in the layers. And that's all there is to it. And so when we did this, we implemented it in TensorFlow because it was the new thing, and it was very scalable. We took some competitors, and we really, we were really fast at converging to good solutions and getting good results. So, and we have an implementation out there in TensorFlow. Unfortunately, I mean, we should now maybe port it to PyTorch, which has become what we work on more. But
no, for sure. But I mean, let's definitely link to that TensorFlow implementation that you have, because I'm very big on pointing people towards how they can apply that in practice, and basically making the bridge between frontier research as you're doing and helping people implement that in their own modeling workflows and problems. So let's definitely do that. And I was actually going to ask you, okay, so that's a great explanation, and thank you so much for laying that out so clearly. I think it's awesome to start from the linear representation, as you were saying, and basically, going to the very big, deep GPs, which are in a way easier for me to represent to myself because they, it's like in the infinity, in the limit. It's easier, I find, to work with than deep neural networks, for instance. But yes, can you give us a lay of the land of what's the field about right now? Let's start with the practicality of it. What would you recommend for people? In which cases would these deep GPs be useful, first? And second question, why wouldn't they use just deep neural networks instead of deep GPs? Let's start with that. I have a lot of other questions, but let's start with that. I think it's the most general one.
Yeah, I think I mean it's a great question. It's the mother of all questions, really. I mean, what kind of model should you choose for your data? And I think there is going to be a lot of great work that is going to happen soon, where we're going to maybe be able to give more definite answers to this. I think we're starting to realize that this overparameterization that we see in deep learning is not so bad after all. So for someone working in Bayesian statistics, I think we have this image in mind where, we should find the right complexity for the data that we have. So there's going to be a sweet spot of a model that is sort of parsimonious in looking at the data and, not too parameterized. But actually deep learning is telling us now a different story, which is not different from the story that we know for non-parametric modeling, for Gaussian processes. In Gaussian processes, we push the number of parameters to infinity, right? And in deep learning, now we're sort of doing the same, but in a slightly mathematical different form. But the so where we're getting at is a point where actually this enormous complexity is in a way facilitating certain behaviors for these models to be able to represent our data in a very simple way. So the emergence of simplicity seems to be connected to this explosion in parameters. And I think Andrew Wilson has done some amazing work on this, and it's recently published. And I can link you to that paper, which says deep learning is not so mysterious. And it's something I was reading recently. It's a beautiful read. And I think, to go back to your question, so today, what should we do? Should we stick to a GP? Should we go for a deep neural network? I think for certain problems, we may have some understanding of the kind of functions we want. And so for those, that if it's possible and easy to encode them with the GPs, I think it's definitely a good idea to go for that. But there might be other problems where we have no idea, or maybe there is too many complications in the way we can think about the uncertainties and other things. And so maybe just throwing a data-driven, if we have a lot of data, maybe we can say, okay, maybe we can go for an approach that is data hungry, and then, we can leverage that. And deep learning seems to be like maybe a right choice there. But of course, now there is also a lot of stuff happening in other spaces, let's say, in terms of foundation models. So now there is this breed of new things, new models that have been trained on a lot of data. And then with some fine tuning on your small data, you can actually adapt them. This transfer learning actually works. And we've done it so there's this paper again by Andrew Wilson on predicting time series with language models. So you take ChatGPT and you make it predict, you discretize your time series, you tokenize, and you give it to GPT, and you look at the predictions, you invert the transformation, so you get back scalar values. And actually, this seems to be working quite well. So we tried now with the multivariate versions of this, probabilistic multivariate, and so on. So we've done some work on that also. But just to say that, now this is something also kind of new that is happening, because before maybe it was really hard to train these models at such a large scale. But now if you train a model on the entire web with all the language is Markovian in a way. So, these Markovian structures are sort of learned by these models. And now if you feed these models with stuff that is Markovian, it will try to make a prediction that is actually going to be reasonable. And this is what we've seen in the literature. And all these things I think are going to change a lot of the way we think about designing a model for the data we have, and how we do inference and all these things. So as of today, I think maybe still is relevant to think about, okay, if I have a particular type of data, I know that, it makes sense to use a Gaussian process because I want certain properties in the functions. I want certain, Matern, for example, gives us some sort of smoothness up to a certain degree. And it's easy to encode length scales of these functions for the prior of the functions. And this is great. For neural networks, this is very hard to do. So we've done some work trying to map the two, right? So we try to say, okay, what can we make a neural network imitate what Gaussian processes do, so that we gain sort of the interpretability and the nice properties of a Gaussian process, but then we also inherit the flexibility and the power of these deep learning models, so that they can really perform well, and also give us sound uncertainty quantification. Yeah.
Okay. Yeah.
Let me show you how to be a good Bayesian.